We kind of travel back in time a bit because one of our speakers unfortunately couldn't make it for his original slot at 1:40, but he made it for the end of the conference, so he'll have the last spot. It's Ralf Klinkenberg from RapidMiner, and he'll be talking about data-driven production process optimization, machine learning, Toolbox, and a use case from the beverage industry. So welcome, so good that you made it to the conference, and for the next 15 to 20 minutes, this stage is yours.
Thank you very much. Yeah, so I have something in common with the previous speaker. I also studied at the University of Dortmund, but it wasn't physics, it was computer science with focus on AI and machine learning. Who am I? Ralf Klinkenberg. I'm one of the two founders of RapidMiner. RapidMiner is a software platform for data science that we started about 20 years ago. And behind that is a company that we started about 15 years ago. RapidMiner is available in an open source version and in various enterprise versions. You can run it on the cloud, on-premise, or on the edge. And yeah, I don't want to talk too much about the company. I'd rather focus on some use cases. Like you can already see in the background of the start slide. The use cases are from the beer brewing industry, but we have use cases across a lot of different industries. Overall, there's more than 1 million registered users in more than 150 countries worldwide in really all of the industries, but there is a heavy focus on manufacturing, industrial production, but also finance, banking, insurance, and many others. So this is joint work with Bitburger Brewery Group. That's why I put another person there as well. He couldn't make it today, but I wanted to have him here anyway because just to show it's joint work. And it's not just me and him, it's actually teams on both sides behind that. Yeah. This started as a research project called DAPRO for data-driven process optimization with machine learning in the beverage industry. So there were a couple of other partners, not only the Bitburger Brewery, but other breweries like Augustina from Munich. There was an industry partner. I'm not sure if you know the brewing industry a little bit. They have machines typically from KHS or Krones. And Krones, again, has a subsidiary called Syskron. They do a lot of innovative IoT and software-related stuff for them. So they were a partner here. And the Technical University of Dortmund and the Research Institute, RIF, located there, were also partners. So what was the whole project about, the motivation and challenges? Beer is a product that come in different qualities. Bitburger, as a brewery group, they have the goal to only provide high-quality beer, so it's a high-quality product. It's a very competitive market, and on the production side, you have the challenge, you have natural ingredients, so there's a lot of variance in the ingredients, and you have to be able to adapt to that. The good thing is they have collected a lot of data over the last 20 years. The process is highly digitized and automated. And there's a lot of potential for process optimization, for example, maximizing the yield of the ingredients like the malt, for energy demand reduction, for cost reductions, for reducing CO2 emissions and other use cases. I will have more on that later. So there's a huge amount of data, there's a lot of potential. Of course, there are some challenges. I will go into those details a bit later. And one of the more recent challenges is actually that the prices of the raw ingredients are increasing. One of the reasons being the Ukraine war, or I should say the Russian invasion of Ukraine. That puts responsibility a bit more clear. That has led to a shortage in supplies, and that has driven prices up. At the same time, you cannot just raise the prices in the market because the competition is so strong. So that has increased the pressure for more efficiency, for cost reductions. And the solution that we designed in this project and implemented prototypically is an easy-to-use machine learning toolbox that can not only be used by data scientists, but also by the domain experts, like the beer brewers, process optimizers, and so on. And also with interfaces, of course, for the machine operators. The idea was we wanted to reduce the effort that is typically needed to go from an idea of a solution to the actual solution using some kind of data mining process, data science workflow, whatever you want to call that. And the goal is to enable the beer brewer, the process engineer, and the others to more easily create their own data analysis based on building blocks that are provided together with experts. And this is to increase the efficiency of the production, to reduce downtimes, and also to gain new knowledge and insights. And one of the goals is, of course, also nowadays and also in the beer brewing industry to increase sustainability, reduce the ecological footprint of the production, for example, CO2 emissions, but there's also other factors that I will mention later on. So going for one topic there is to reduce the amount of raw ingredients needed. For example, to reduce the amount of malt needed in the brewing process. Maximizing the yield of that means I have lower need for the raw material. That means the ecological footprint is smaller. I need to produce less. That means I need to grow less. Needs less area, less energy, less water, and also needs less means of transportation because I need fewer trucks. So again, less energy needed there. So if I can be more efficient in my material use, I can obviously lower CO2 emissions as a side effect. Similarly, if I can make my production processes more efficient, I can also reduce the CO2 emissions there. And so predicting and lowering the energy consumption is also a major goal, both from the financial point of view as well as from the environmental point of view. And I just give some examples in a bit more detail shortly. One is the malt yield forecasting for different mixtures of malts. Like I said in the beginning, that one of the challenges is we have natural ingredients, we have different suppliers, they grow the malt in different regions, different types of malts, and for the beer I have to mix that in a mixer that first of all tastes good, of course, has a high quality, but also, has a high yield. I don't want to waste raw material unnecessarily. And not only the malt parameters are important there, but also the process parameters, like how I set up the machines, the speed of things, how much time I allow the process to extract the taste from the malt, and so on. And the other aspect we focused on a bit more was also energy demand forecasting, especially for cooling, because cooling in the beer industry is the biggest energy consumer, like cooling the beer when it's young and fresh, but also cooling it when you store it for longer. And if you have forecasting models for the energy demand, you obviously can try to adapt things, be more forward-looking. Instead of producing more cold than you need or more energy than you need, you can actually avoid unnecessary peaks and unnecessary production. For those that are interested in the domain side of it, this is a visualization of the beer brewing process. The ingredients and the machine learning use cases you can do. This is only a small selection. We have identified about 50 use cases in the beer brewing industry that you could do with machine learning. We then discussed that together with the expert, which ones to focus on, and those are the ones that we are most interested in for now. So malt yield prediction and optimization is obviously one of them. Then predicting certain properties of other ingredients in the beer brewing process is another. For example, predicting the alpha content of the hop, another important ingredient. And then talking about ingredients, we have the malt, we have the hop, then there's obviously water, and then there's yeast. For those that are not so firm with the English terms, for the beer brewing, I also added the German terms in parentheses, especially when you look at the process steps like milling, mashing, lautering, and so on. I find that hard without looking it up myself sometimes. So this is a bit of a bilingual slide. So in the middle, you see the process steps. In the top, you see the ingredients going in, and then you see the use cases around it. So energy demand forecasting, demand peak prediction, and avoiding them. That is one use case. At the end of the production line, you have the customers, and now in some industries, customers are nice. They order in advance what they want, and so you can plan your production. The problem in the beer brewing industry is they don't order in advance usually. They just send a truck and say, please fill it up. And then you have to fill the whole truck with beer bottles or cakes of beer and so on. And there's obviously not only one truck coming, there's lots of trucks. So you actually try to predict how many trucks will there be, at what time, how much do I need to produce, how can I organize it, maybe can I give them a guidance when they should come or rather not come if they don't want to wait too long. So it's also very interesting there. Then predictive maintenance, like we heard before, predicting machine failures to avoid them, to optimize the maintenance, like do not do maintenance more often than necessary, but do it often enough so nothing breaks and the product quality stays high. Estimation of filter lifetime, like predicting how long you can use a filter before you have to replace it, is another expensive part in the production. And then another example is predicting basically filter downtimes or downtimes in the process before the bottle filling that can create downtimes at the bottle filler. which itself is a bit of a sensitive part, but there's also other sensitive parts. So there's, a lot of use cases. This is, like I said, just a small set of examples. You don't have to read all of the text. You can have the slides afterwards if you want. This is just a visualization of how you create the cool. You have a cooling fluid, and by increasing the pressure, you can actually cool it down. And if you need more cooling, then you increase the pressure. But obviously for that, you need more energy. And that's why this is one of the most energy-intensive parts of the beer production process. And typically, there's not just one compressor. There's a whole series of compressors. And if you need more cooling, then you just start another compressor. And if you predict you will need a lot, then you start more. But if you could actually predict it's just a very short peak, you don't really have to have more compressors, then maybe you just don't start another one. You can actually avoid the peak, and you can avoid the unnecessary energy consumption. So that's basically, in a nutshell, what this use case is about. Turns out it's quite complicated because there's a lot of influence factors, and even for the domain experts, the beer brewing experts, it's not easy to say when a peak would have been avoidable and when not. So this is actually quite a challenging use case. The data we used is obviously from the big energy consumers, like the compressors for the cooling, but also over time we want to add more and more of the smaller consumers. And obviously the overall consumption is a target that we try to predict and to minimize. The other use case I dive in a little bit deeper is the malt yield prediction for different mixtures of malt, so that we can minimize the consumption of raw materials, or in other terms, maximize the yield of the malt. Like I said, it's a natural raw material. There's fluctuations, different suppliers, different regions where it's grown. So the idea is to, for different combinations of malts in different quantities, and for different parameters of the production process, predict how much yield you will have, so that you can actually simulate different settings and then pick the best one. And that way, I'll maximize the yield. There's a little bit a visualization of that process. You have the data set with the malt specifications for the different malts. You have information about the silos where the malt is stored. Maybe you have 10 different silos, and then you always put the new malt on top, and it goes down at the bottom. And then you have lab results from your tests, what the quality parameters are, including the yield. The problem is, at the time when you have the lab results, it's already too late. You want to control the process early on. So the challenge is actually you have to predict the target, the malt yield, as early as possible with as few of these data points as possible. But that works actually quite well. I have some examples of how this is being deployed later on. And now, like I said, we want to not only data scientists be able to design these kind of processes, but we actually want the domain expert, the beer brewer or the process engineer, also to be able to do that. And for that, we try to standardize data mining processes for particular industry-specific use cases. Of course, like we heard before in the talk, there's no black box that solves all use cases perfectly. That's why we said for this industry, we start designing a solution catalog of different use case solutions, and then it makes it much easier if you have already a solution that just needs to be tailored to the data points that you have available. That's basically that. There's customized data pre-processing, there's customized model creation with something like an auto model in the background, and then at the end there's also support for deploying that. And the beer brewer should be able to answer a lot of questions like, how can I have this data, how can I gain insights? And then you can look at the catalog of solutions. And then you also get explanations of what the results tell you, if they make any sense. Let me skip a bit ahead. The overall toolbox, like I said, is a solution catalog for different use cases. I just show some here. And it's something that's growing. It's a work in progress in a sense. Then there's a data aid in the sense that it helps you to connect your data to a predefined data schema for that use case. So that use case is supposed to be generic, transferable, so it scales across your organization, different factories, different brands, maybe across companies even. So that there's some a generic part of a use case solution, but then you have your own data in its own formats, in its own sources, and you have to connect that somehow. For that, we use data schemas, and we use semi-automated data mapping. That means the system automatically tries to match and gives you recommendations what to connect, and then the matching after that can be automated in the future. There's an analysis configurator. It's a very modular approach, like a Lego toolbox, but on a very high level of use case components. There's a validation assistant that checks if your data matches the schema. If there's type mismatches, then it tries to automatically transform that. If there's missing values, if that is a problem or not, and so on. It suggests solution like missing value handling, like interpolation, for example, or using machine learning to predict missing values or something like this. Then there is support for the model deployment, just a few clicks away. And there's also support for model understanding and interpretability. Like we heard by the previous speaker, you don't want a black box. You want to understand your data. You want to understand the solution, the model, and the prediction, the recommendation, because you usually only trust it if you understand it. At least you should. So you have a catalog of solutions. This can be tailored to your data using these assistant systems. And maybe I should say a word about RapidMiner here. RapidMiner is a platform, very generic, with more than 100 machine learning algorithms. You can do your own coding in Python or R, but you don't have to. We usually use a visual approach to data mining process design. Nowadays it's called low code or no code, or you use something like an auto model. So that's in the background. And now the modules you built here are a level higher. They're on the use case level or use case component level. So this is what the visual data science process might look like. And now there's new steps that we added. For example, something like create data schemas. So an expert can actually create a schema for a certain use case. The data scientists defined what the schema is, data types, names, interpretations, and so on. And then the beer brewer has his own data, different format, needs to be adjusted. So there's this module that supports the adjustment and data transformation and actually does it in the background, creates a process that you can, as an expert, if you want to, also modify. We skip a bit faster. Like I said, there's an automated process generation going on in the background for those who want to see it, but you don't have to look at it if you don't want to see it. You can validate your data to the schema, and then you can connect your own data to the data schema. Once you've done that, you can use the use case module. Let me skip a bit faster here, and then go back to the use cases. So for the malt yield prediction, an acceptable range of yield is 70 to 80% yield. And we were actually able to predict that very close with a relative error of only 0.6% for different malt mixtures and different process configurations. And that was already in a pre-study that we did. And then we obviously optimized that further in the project. For those interested, we used different machine learning techniques that worked best there with different decision tree-based learners like random forest, generalized linear models were also very successful. And yeah, what was always key also, we wanted to have models that are transferable across different batch lines for the brewing, different factories, and even companies. Like I said in the beginning, there were different breweries in the project. In the deployment of the yield prediction, you can, for example, see what the mixture is. So the blue columns indicate the different silos. Each silo has a different malt in it, maybe even a mixture of malt if you fill different malts into that silo. Then you see at the bottom how much what percentage of each malt you want to use for your mixture, and then at the right you see the prediction what the yield would be. You can change the mixture and you see again the prediction of the yield, so you can optimize the yield. So that's one way of looking at it. Another view is a dashboard for the brewer and the machine operator that shows all the relevant parameters. At the top again you see the mixture of malts, and then you can look closer into each silo. Here's a open up for silo 2, where you see, okay, what malt do I have there? What are the measurement of quality parameters of that malt, and so on. And at the right side, it's a bit hard to read probably on the distance, you have the same forecast again. It's just a different view for a different user group. Okay, we also have auto modeling tools involved, and we have modules for simulating based on these generated machine learned models, where you can play with the parameters of the process. You can say, what happens if I change this? What happens to my yield? You see what were the most important influence factors for that prediction. So it helps you to understand what are the key factors in that particular setting, and are they impacting my yield positively or negatively? Thank you very much for the attention. We had some takeaways in the previous talk, and I actually would subscribe to those, very well presented. So mine are a bit shorter, but they're basically along the same lines. You need domain expertise on the one side, you need data science expertise on the other side, and obviously need to collaborate if you want to have a high quality solution at the end. The learnings from the industry side, from the beer brewers, was the amount of data is not equal to the amount of information you gain, because they had data from 20 years, from all the processes they did, but they didn't extract much information from it. So they first had to basically set up a data science environment and infrastructure so they can make use of that data. But the big plus that they had is their domain expertise. And on our side, we as a data scientists, obviously we need to collaborate. We're no beer brewers. We know the process a little bit, but still we're no beer brewers. So we need their domain expertise. We need their data. We then have the algorithms for that. We have the expertise in AI and machine learning. Our goal was to create tools that are usable for non-data scientists, and I hope the screenshot showed a little bit how that looks like. Important was scalability and transferability to other factories, to other breweries. And I showed on the use cases, you can often have a win-win situation. You can increase efficiency, lower cost, at the same time also lower CO2 emissions, lower energy consumption. So there's very attractive win-win situations. Thank you very much for your attention. If you want to know more, there are some links in there where you find more about the project, also more about the organizations involved, and you can also send me an email and ask for the slides or more details later on. Thank you very much.
Thank you very much, Ralf. And this will be my last time asking you if there are any questions. There are. So David is answering. And please quickly say who you are and what company you're representing.
So I'm Nima Siboni. I'm representing InstaDeep, but I have a question, which is I did a project which is kind of similar optimization of a process, which is recycling process. There you have also recycling of metals, let's say. And there we have the very similar situation that you get a batch of scrap metals and you don't know what's the ingredients there. Comes in very different compositions. But there we have the problem that, and we address that problem with reinforcement learning, and it kind of works nicely. We can optimize for CO2 emission and also getting the desired final product. But there the processes have way more nuanced than being able to put into a couple of numbers. Is it also the case in this industry that, because you presented the processes with a couple of numbers, and usually this is not the case?
Yeah, that's a very good observation. That's actually true. Like some use cases luckily can be done with numbers, and some of the beer brewing use cases are nice and numeric. But in a lot of industry use cases, we have textual data, like for example, operator notes that the operator observed some weird noise, some vibration, some product quality issues, and he just takes notes. And you can make use of text data as well. You can make use of audio data. For example, when you do predictive maintenance, a lot of machines have, for example, increased vibrations before they fail, and you can either measure that with vibration sensors or you can use audio sensors, and then sometimes you hear like maybe a deeper sound or a high-pitched sound that gives you some clue that something is not right there. Then you can use image data. That's used a lot in product quality analysis, product quality prediction. We've also done projects in the metal industry, for example, with ArcelorMittal, the world's largest steel producer, which was about quality prediction as early on in the process. So again, they don't have to do the follow-up steps, save a lot of energy by not doing them. And we've done projects in the chemical industry, and there the data was really mixed. A lot of textual data, lab data, measurements data, facility design data. There can be all kinds of things that you have to kind of merge. The nice thing is in the background, RapidMiner is a tool that has hundreds of data connectors, hundreds of modeling algorithms. You can build almost anything you want if you have the expertise and the time. The goal now was here a bit to not only support this very thorough, long-lasting projects, but rather help the domain experts to do something quickly, try to find standardizable things. Not everything is standardizable, that's for sure. And both is probably worthwhile pursuing. It just might be different people. In one case, you need a full team for maybe a year even. And in other cases, if it's standardizable, maybe you just need a few clicks and a day or two. And then you at least have a certain baseline solution, which of course you can then optimize. So yeah, having open systems that allow all these kinds of integration of additional data is super important. Yeah.
Thank you.
And there was another question in the back.
Yeah, hi, Mathis Börner, SAP. Were you able to quantify the ecological benefit of your effort?
Not yet. Like for the malt yield, we know that it has an impact, but I don't have the number as a CO2 emission reduction, for example, yet. That part is still ongoing. Like we have done the let's say, data science evaluation. We know that we can accurately predict it. We have a statement from the beer brewers, how much they think they will be able to save in terms of euros or in how much more yield they will have. But we don't have numbers for the CO2 emission yet. It's a bit too early yet still. Like RapidMiner as a company, we do it for ourselves already. Like we started this year to compute our own CO2 emissions, but it's a bit easier because, yeah, as a software company, you have like office, mainly heating costs. They have IT costs in the cloud or on site. You have travel costs, and this is all very well defined and easy to compute. For these complex processes, it becomes much more complex. But we're on it. Like we're looking with reference customers at the topic, like how can we compute their footprint to also measure how can they improve it. It's a big topic.
Okay, and for the malt year, do you have like a ballpark of how much efficiency increasement you were able to achieve?
It's still ongoing, but so far we expect like 20% in that ballpark range. It's not a final number yet, like I said, but that would be something we expect.
Thank you very much. Are there any other questions? That's not the case, so thanks for being our last speaker, and thank you for taking your time to join us, even if it was later than planned. I guess it was really insightful, and good luck in the future with all of that. Thank you very much.
Thank you a lot for having me.